Welcome to Science Snippets Fun Facts and Trivia. Today, we bring you, is time travel possible? The reality of time machines explained by modern physics. Chapter 1: The fascination with time travel. Section 1: Why time travel captivates us. Time travel is one of humanity's most intriguing fantasies. From ancient myths to modern movies, the idea of stepping into a machine and traveling backward to relive history or forward to witness the unknown future has always captured our imagination. But why does this concept resonate so deeply with us? To answer that, we need to look at the emotions and curiosity driving this fascination. For starters, time travel appeals to our desire to fix past mistakes. Imagine being able to undo a decision, repair a relationship, or even prevent a historical catastrophe. This "what if" factor is an irresistible thought experiment for many. It reflects our longing for control over life's uncertainties and regrets. Could we rewrite history to make the present better, or would our interference lead to unintended consequences? The emotional weight of these questions makes time travel more than just a scientific idea. It's a deeply personal one. But the allure of time travel isn't just about the past. It's also about the future. Humans are natural explorers, constantly seeking answers to what lies ahead. What kind of world will we leave for future generations? Will technology advance beyond our wildest dreams? Or will we face existential challenges like climate change or resource scarcity? Time travel offers a shortcut to those answers, satisfying our hunger for knowledge about the unknown. There's also a philosophical side to this obsession. Time is a mystery that governs our lives, yet we barely understand it. Why does time seem to flow in one direction, like a river? Could it ever flow backward? These questions challenge the way we perceive reality. The possibility of time travel pushes us to rethink the nature of existence itself, turning an abstract idea into a profound intellectual journey. Finally, there's the undeniable thrill of adventure. Time travel promises not only answers to big questions but also incredible experiences. Meeting dinosaurs, walking through ancient civilizations, or witnessing the birth of the universe. These scenarios spark wonder and excitement, taking us beyond the limits of the present and into realms that feel magical, even if they're rooted in science. In essence, time travel captivates us because it's a perfect blend of our deepest emotions, intellectual curiosity, and love for adventure. It gives us hope for second chances, excitement about the future, and an escape from the limitations of our current world. Whether through science, storytelling, or sheer imagination, the concept of time travel will always remain a source of fascination. Section 2: Time travel in popular culture. When it comes to time travel, one of the most influential drivers of our fascination has been popular culture. Movies, books, TV shows, and even video games have shaped the way we think about bending the laws of time. They have inspired generations to imagine not only the scientific possibilities, but also the emotional and moral dilemmas that could arise from tampering with time. The concept of time travel first gained traction in literature. H.G. Wells' 1895 novel The Time Machine is often credited with popularizing the idea in modern storytelling. In this groundbreaking work, Wells explored the potential for a device that could take its user far into the future or deep into the past. But it wasn't just about the mechanics of time travel. Wells used it as a lens to critique society, focusing on class struggles and humanity's possible future. Since then, time travel has remained a powerful storytelling tool for examining human nature and the consequences of our actions. In film, time travel has taken on a life of its own. Who can forget Back to the Future, the 1985 blockbuster that redefined the genre? Marty McFly's adventures with Doc Brown not only made time travel fun and thrilling, but also introduced audiences to the dangers of altering the past. Movies like Terminator and Interstellar added a darker, more philosophical edge to the concept. They asked critical questions: could altering time save humanity? Or would it doom us? How does time work on a cosmic scale? These stories demonstrate how time travel can spark not just our imaginations but also our existential thinking. Television has also played a crucial role in keeping time travel relevant. Shows like Doctor Who made it a central theme, with the Doctor traveling through time to explore different eras, civilizations, and moral dilemmas. Meanwhile, modern series such as Dark delve into the complexities of time loops and paradoxes, portraying time travel as both a gift and a curse. These shows keep viewers hooked by blending science fiction with emotional depth, making time travel feel relatable yet mysterious. Video games have added an interactive element to the concept, allowing players to directly experience the thrill of manipulating time. Games like Chrono Trigger and Life is Strange let players alter timelines and see the consequences of their decisions unfold. This interactivity has brought a new level of engagement to the age-old question: if you could change the past, would you? Popular culture doesn't just entertain us. It shapes how we understand and imagine the possibilities of time travel. Through stories, we explore what it means to break the boundaries of time, asking both what could be and what should be. It's a testament to how deeply ingrained the idea of time travel is in the human psyche, constantly inspiring new generations to dream about the impossible. Section 3: What science has to say about time travel. Time travel has long been a staple of science fiction. But how does it stand up to real scientific scrutiny? For years, physicists and mathematicians have explored the possibility of moving through time, not as a fantasy, but as a phenomenon grounded in the laws of nature. While it might sound like science fiction, modern theories suggest that time travel may not be entirely impossible, though it comes with significant challenges. The foundation for scientific discussions about time travel lies in Albert Einstein's theory of relativity. According to his groundbreaking work, time is not an absolute, fixed concept. Instead, it is flexible and relative, depending on factors like speed and gravity. For example, time slows down the closer you get to the speed of light, a phenomenon known as time dilation. Astronauts aboard the International Space Station experience this effect, aging slightly slower than people on Earth. While this is a small-scale example, it demonstrates that time is not as rigid as we once thought. Another concept that sparks hope for time travel is the existence of wormholes, also called Einstein-Rosen bridges. These theoretical structures are shortcuts through space and time, connecting distant points in the universe. If wormholes exist and could be stabilized, they might serve as tunnels for time travelers to journey to the past or future. However, the energy required to keep a wormhole open would be astronomical, involving exotic materials that have yet to be discovered or understood. Black holes, another fascinating element of Einstein's theory, also hold potential clues about time travel. The immense gravitational forces around a black hole can warp time dramatically. In theory, if you could survive the extreme conditions near a black hole, you might experience time much more slowly than someone far away. This would allow you to travel into the future, though returning to your original time would remain a significant challenge. Quantum physics adds another layer of complexity to the discussion. At the quantum level, particles, behave in ways that defy our traditional understanding of cause and effect. Some scientists speculate that quantum entanglement, where particles influence each other instantaneously over vast distances, might hint at mechanisms for manipulating time. However, these ideas remain highly speculative and far from practical application. Despite these fascinating theories, time travel faces enormous obstacles. Paradoxes, such as the grandfather paradox, raise questions about whether altering the past could disrupt the present. Additionally, the energy requirements for any practical time travel scenario are so vast that they exceed anything humans can currently produce. Finally, our limited understanding of time itself makes it difficult to determine whether backward time travel is even theoretically possible. In summary, while science has provided glimpses of how time travel might work, the road to making it a reality is still a long one. Theoretical physics offers intriguing possibilities, but for now, time travel remains an idea that exists more in equations than in practice. Still, as our understanding of the universe deepens, who knows what breakthroughs the future might hold. Chapter 2: Understanding Time Itself. Section 1: What is time? Philosophical and Scientific Perspectives. Time is one of the most mysterious and fundamental aspects of our universe. We experience it every day, but when we try to define it, it becomes surprisingly elusive. Philosophers and scientists alike have grappled with the question for centuries: what is time, and why does it move the way it does? Philosophically, time has been debated since ancient Greece. Some philosophers, like Heraclitus, believed that time flows continuously, like a river. Others, like Parmenides, argued that time is an illusion, and everything exists all at once, unchanging. These ideas laid the groundwork for modern theories that question whether time is something we experience subjectively, or whether it exists as a fundamental property of the universe. Science offers a more concrete perspective, though it is no less mind-bending. In the 20th century, Albert Einstein revolutionized our understanding of time with his theory of relativity. He showed that time is not constant. Instead, it is intertwined with space, forming what we now call spacetime. According to Einstein, time moves differently depending on speed and gravity. For example, the faster you move, the slower time flows for you, relative to someone standing still. This phenomenon, called time dilation, has been confirmed through experiments, such as observing the behavior of atomic clocks on fast-moving planes. Another scientific insight is that time seems to have a direction: a past, present, and future. This arrow of time is closely linked to entropy, the measure of disorder in a system. According to the second law of thermodynamics, entropy tends to increase over time, which is why we perceive time as moving forward. However, this doesn't explain why the universe started with such low entropy, or whether the arrow of time could ever reverse. Despite these advancements, time remains a profound mystery. Is it a physical property that can be measured, or is it simply a construct of human consciousness? Modern physics suggests that time may not be as fundamental as we think. Theories like quantum gravity propose that spacetime itself could emerge from more basic principles, meaning time might be an approximation rather than an absolute reality. In short, time is both simple and complex. We measure it with clocks and live our lives by it, yet its true nature continues to puzzle even the brightest minds. Understanding time is not just about science. It's about understanding our place in the universe. Section 2: Einstein's theory of relativity and time dilation. Albert Einstein's theory of relativity revolutionized our understanding of time. Before his groundbreaking work, time was thought to be absolute, an unchanging backdrop against which events unfolded. However, Einstein showed that time is not fixed but relative, depending on factors like speed and gravity. This discovery completely changed the way we think about time and space. The key idea in Einstein's special theory of relativity is that the speed of light is constant for all observers, no matter how fast they are moving. To maintain this constancy, time itself must adjust. For example, imagine two clocks, one stationary and one moving close to the speed of light. According to Einstein, the moving clock will tick more slowly than the stationary one. This effect, known as time dilation, has been confirmed by experiments using atomic clocks on airplanes and satellites. Time dilation doesn't just exist in theory, it has practical implications. For astronauts traveling at high speeds in space, time would pass more slowly compared to people on Earth. While this effect is minor at everyday speeds, it becomes significant at velocities approaching the speed of light. This means that for a space traveler, a journey lasting only a few years could result in decades or even centuries passing on Earth. It's a concept often explored in science fiction, but it's also grounded in real physics. Einstein's general theory of relativity takes this further by showing how gravity affects time. Massive objects, like planets or stars, warp the fabric of space-time, creating what we perceive as gravity. This warping also slows down time. For example, clocks closer to a massive object, such as the surface of Earth, tick more slowly than clocks farther away. This phenomenon, called gravitational time dilation, has been measured with incredible precision using satellites in orbit. These insights are not just theoretical, they are essential for technologies like GPS. Satellites in orbit experience both gravitational and velocity-based time dilation, causing their clocks to run slightly faster than those on Earth. Engineers must account for this difference to ensure GPS systems work accurately. In essence, Einstein's theory of relativity revealed that time is far more flexible than we ever imagined. It bends, slows, and stretches depending on the conditions. While we experience time as something steady and predictable, relativity reminds us that this is only a small piece of the bigger picture. Section 3: How time behaves in extreme conditions. While time feels stable in our everyday lives, it behaves very differently in extreme environments. Whether it's the immense gravitational pull of a black hole, or the incredible speeds of particles near the speed of light, time can warp, slow down, or even seem to stand still under these conditions. These phenomena give us fascinating glimpses into the flexible nature of time. Let's start with black holes, one of the most extreme environments in the universe. A black hole's gravity is so strong that it warps space-time around it. Close to the event horizon, the boundary beyond which nothing can escape, time slows down drastically compared to the outside world. To an observer far away, a person approaching the event horizon would appear to move slower and slower, as if frozen in time. However, for the person near the black hole, time would seem to pass normally. This time dilation near black holes isn't just theoretical. It's supported by Einstein's general relativity and has been depicted in movies like Interstellar. Another extreme condition is traveling at speeds close to the speed of light. According to special relativity, as an object's speed increases, time for that object slows down relative to a stationary observer. This effect is more than just a theory. It has been observed in experiments with high-speed particles. For example, Subatomic particles called muons, created in Earth's atmosphere, decay more slowly when moving at near light speeds than when stationary. This time dilation allows them to travel further than they otherwise could before decaying, a phenomenon that matches Einstein's predictions perfectly. Time also behaves strangely on a cosmic scale. In regions of the universe with extremely strong gravitational forces, such as neutron stars, time moves more slowly than it does in less dense areas. This effect, though less pronounced than near a black hole, still demonstrates the connection between gravity and time. Interestingly, these extreme conditions also influence the universe's overall structure, such as how galaxies form and evolve over billions of years. Lastly, extreme conditions also include the microscopic world. In quantum mechanics, the concept of time is far less clear. Some theories suggest that time, as we know it, might emerge from deeper, more fundamental processes at the quantum level. This challenges our understanding of time as a universal constant, and opens the door to new theories about its true nature. In extreme environments, time doesn't behave in the linear, predictable way we experience in daily life. Instead, it bends, slows, and stretches in ways that defy intuition. These extraordinary behaviors remind us that our everyday experience of time is only a small part of a much stranger and more complex reality. Chapter 3: The Science Behind Time Travel. Section 1: Wormholes, a possible path through time. Wormholes, often called Einstein-Rosen bridges, are one of the most fascinating theoretical concepts in physics. They represent potential shortcuts through space-time, connecting distant points in the universe. But what makes wormholes even more intriguing is the idea that they could be used for time travel, if we could figure out how to create and stabilize them. The concept of wormholes comes from Einstein's theory of general relativity. According to this theory, massive objects warp space-time, and under certain conditions, it's possible for two distant regions of space-time to become connected by a tunnel-like structure. Think of space-time as a sheet of paper. If you fold it so that 2 points touch, a wormhole could theoretically link those points, allowing a traveler to move between them instantly, rather than crossing the vast distance in normal space. But how does this relate to time travel? In theory, if one end of a wormhole were kept stationary, while the other were moved at near light speeds, time dilation would come into play. The moving end would age more slowly than the stationary one. As a result, the two ends of the wormhole would exist at different points in time. If you were to travel through the wormhole, you could theoretically emerge in the past or future, depending on how the two ends were manipulated. Of course, there are enormous challenges to making this a reality. For one, no evidence of naturally occurring wormholes has been found, and creating one would require exotic materials. These materials, often called negative energy or exotic matter, would need to counteract the immense gravitational forces that would normally cause a wormhole to collapse. So far, scientists have only observed tiny amounts of negative energy under very specific conditions, making this a major hurdle for time travel through wormholes. Another challenge is stability. Even if a wormhole could be created, it would likely be incredibly unstable. The slightest disturbance could cause it to collapse, trapping, or worse, destroying, anything inside. This raises questions about whether wormholes are a practical solution, or just a theoretical curiosity. Despite these obstacles, the idea of wormholes remains a popular topic of research and imagination. They offer a tantalizing possibility for overcoming the vast distances of space and even breaking the barriers of time. While we are far from turning wormholes into functional time machines, their existence would open up an entirely new understanding of the universe and our place within it. In summary, wormholes represent a potential pathway through both space and time, but for now, they remain firmly in the realm of theory. As our knowledge of physics grows, who knows what discoveries may lie ahead? Section 2: Black holes and gravitational time distortion. Black holes are some of the most mysterious objects in the universe, and their influence on time is nothing short of extraordinary. These cosmic giants warp spacetime to such an extreme degree that time itself slows down near their boundaries. Understanding how this works brings us closer to grasping the strange relationship between gravity and time, and why black holes might hold clues about time travel. The immense gravity of a black hole comes from its incredible density. Imagine a star many times the mass of the Sun, collapsing into a point so small that it creates a region where gravity is virtually inescapable. This region is known as the event horizon, the point of no return. Near this boundary, the gravitational pull is so strong that it stretches and distorts space-time, causing time to move more slowly compared to areas further away. To an outside observer, someone approaching the event horizon would appear to move in slow motion. As they get closer, their movements would seem to almost freeze, as if time has stopped. However, for the person falling into the black hole, time would pass normally. This phenomenon, known as gravitational time dilation, is a direct result of Einstein's general theory of relativity. This concept is not just theoretical, it has practical evidence. Scientists have observed time dilation near massive objects like stars and planets, though on a much smaller scale. For example, clocks placed on the surface of Earth tick more slowly than those on satellites in orbit, where gravity is weaker. Near a black hole, this effect becomes extreme, making it a natural laboratory for studying the flow of time. But how does this relate to time travel? The slowed passage of time near a black hole creates the potential for what's called time displacement. If a spaceship were to orbit close to a black hole for what felt like a few years, thousands or even millions of years could pass for observers far away. In essence, this is a one-way trip into the future. However, traveling back to the past remains an entirely different challenge. Movies like Interstellar have popularized this idea, showing how black holes could allow humans to experience time in ways that defy intuition. While these depictions take some creative liberties, they are rooted in real science, showcasing just how strange time can become under extreme gravitational conditions. Despite their dangers, black holes offer a unique window into the mechanics of the universe. They stretch the limits of our understanding of time and space, reminding us that what seems impossible might one day be within reach. As our tools for studying these cosmic giants improve, we may uncover even more surprising connections between black holes and the mysteries of time. Section 3: Closed time-like curves. Science or science fiction? The idea of closed time-like curves (CTCs) might sound like something straight out of science fiction, but it's a concept rooted in Einstein's general theory of relativity. These theoretical paths through spacetime could, in theory, allow an object, or even a person, to travel back to an earlier point in time. But how realistic are closed time-like curves? And could they ever lead to practical time travel? A closed time-like curve is essentially a loop in spacetime. Imagine bending spacetime so much that a path through it brings you back to the same point in both space and time, much like walking in a circle. This is possible in mathematical models of general relativity, particularly in scenarios involving extreme gravitational forces or space-time distortions. One famous example is the solution proposed by Austrian physicist Kurt Gödel in 1949, which described a rotating universe, where closed time-like curves could theoretically exist. Another potential source of closed time-like curves involves wormholes. As mentioned earlier, if one end of a wormhole experiences time dilation relative to the other, it could create a path where traveling through the wormhole allows you to arrive at an earlier time. However, this idea, while fascinating, runs into significant challenges. Stabilizing a wormhole and preventing it from collapsing under the influence of gravity would require exotic matter with negative energy, something we've yet to produce in sufficient quantities. One major complication with closed time-like curves is the paradoxes they introduce. The grandfather paradox, for instance, asks what would happen if you traveled back in time and prevented your own birth. Would the timeline correct itself, or would reality, as we know it, break down? Some physicists propose that CTCs might avoid these paradoxes by following self-consistent rules, meaning any actions you take in the past would already be part of history and could not alter the future. This is sometimes called the Novikov self-consistency principle. Despite these intriguing possibilities, many scientists remain skeptical about the practicality of closed time-like curves. Quantum mechanics, which governs the behavior of particles on the smallest scales, complicates matters further. Some theories suggest that quantum effects might prevent the creation of CTCs altogether, effectively blocking time travel. Others argue that the energy required to form a closed time-like curve would be so immense that it's beyond anything we could achieve. So, are closed time-like curves science or science fiction? At this point, they exist firmly in the realm of theoretical physics. While they are mathematically possible within Einstein's equations, the physical conditions required to create them are far beyond our current capabilities. For now, they remain a tantalizing concept, inspiring both scientific research and imaginative storytelling. Chapter 4: The Paradoxes of Time Travel. Section 1: The Grandfather Paradox Explained. Time travel to the past introduces one of the most famous thought experiments in theoretical physics, the grandfather paradox. This paradox challenges the very concept of altering the past and raises deep questions about how time and causality work. So, what exactly is the grandfather paradox? And why does it remain a key obstacle to understanding time travel? The paradox begins with a simple premise: what if you traveled back in time and accidentally, or deliberately, prevented your grandfather from meeting your grandmother? If this event were altered, one of your parents would never be born, and by extension, neither would you. But here's the catch: if you were never born, how could you have traveled back in time to begin with? This creates a logical loop, where the act of traveling to the past erases the very possibility of your time travel in the first place. At its core, the grandfather paradox exposes the contradictions in the idea of changing past events. If time travel allows you to alter history, it creates inconsistencies that defy logical causality. These contradictions make physicists question whether time travel to the past is possible, or whether there are mechanisms in place, natural or otherwise, that prevent such changes from occurring. One way to resolve the paradox is through the idea of self-consistency, as proposed by the Novikov self-consistency principle. According to this theory, even if time travel to the past were possible, any actions taken by the time traveler would have to be consistent with the events that have already occurred. In other words, the timeline cannot be changed. For example, even if you attempted to prevent your grandfather from meeting your grandmother, circumstances would conspire to ensure that their meeting still happens, maintaining the integrity of the timeline. Another potential solution involves the multiverse hypothesis. This theory suggests that any changes made in the past would not affect your original timeline, but would instead create an entirely new parallel universe. In this scenario, you might prevent your grandfather from having children in the new timeline, but your existence in the original timeline would remain unaffected. While this idea resolves the logical inconsistency, it requires the existence of multiple universes, a concept that remains highly speculative. Despite these proposed solutions, the grandfather paradox highlights the complex and often counterintuitive nature of time. It forces us to confront the limits of our understanding and explore whether the rules of causality, as we know them, can bend or break under certain conditions. In the end, the grandfather paradox serves as a reminder that time travel to the past is not just a question of technology, but one of profound philosophical and scientific challenges. It's a puzzle that continues to intrigue scientists and storytellers alike, keeping the dream of time travel alive, while also reminding us of its potential pitfalls. Section 2: The bootstrap paradox. Can something create itself? The bootstrap paradox is one of the strangest and most puzzling ideas in time travel theory. It asks a simple yet mind-bending question. What happens if an object or piece of information creates itself through time travel? This paradox challenges our understanding of causality and raises profound questions about the nature of time and existence. Here's a classic example. Imagine a scientist who receives the plans for a time machine from their future self. Using these plans, they build the machine, travel back in time, and hand the same plans to their past self. The question is, where did the plans originally come from? If they were passed in a loop between the scientist's future and past selves, they seem to exist without an origin, defying the traditional flow of cause and effect. This paradox isn't limited to objects, it also applies to knowledge. In the TV series Doctor Who, for instance, the bootstrap paradox is illustrated through Beethoven's music. A time traveler, unable to find Beethoven in the past, introduces his music to history, becoming the source of the composer's work. But if Beethoven never wrote the music, who truly created it? The bootstrap paradox raises a fundamental issue. Can something exist without an identifiable beginning? Some physicists suggest that the universe itself might be a giant bootstrap paradox. If time loops exist, they could allow for self-contained cycles of events, though this idea remains purely speculative. Resolving the paradox often involves theories, like the Novikov self-consistency principle, which asserts that time travel events must be consistent with history. In this view, the plans for the time machine always existed in the timeline, and their origin is simply a closed loop. Others turn to the multiverse theory, proposing that such paradoxes are avoided because the timeline splits into parallel realities. While the bootstrap paradox stretches our imagination, it also reveals the limits of our understanding of time. It's a puzzle that invites us to think deeply about causality and whether the universe might allow for such strange loops in reality. Section 3: Solutions to these paradoxes. Time travel paradoxes, like the grandfather paradox and the bootstrap paradox, are fascinating yet frustrating challenges for scientists and philosophers. They highlight the potential logical inconsistencies of altering the past or creating self-contained time loops. However, several proposed solutions attempt to resolve these paradoxes. offering us possible ways to reconcile time travel with the laws of physics. One prominent idea is the Novikov self-consistency principle, which suggests that paradoxes simply cannot occur. According to this principle, the timeline is self-consistent, meaning any actions a time traveler takes in the past are already part of history. For example, if you travel back to prevent your grandfather from meeting your grandmother, circumstances will always conspire to ensure their meeting happens. You might accidentally be the one who introduces them, making the paradox impossible. This approach removes contradictions by assuming the universe enforces logical consistency. Another potential solution involves the multiverse theory. This idea proposes that every change to the timeline creates a new, parallel universe. If you traveled back and altered the past, you wouldn't erase your original timeline. Instead, you would create a new one where events unfold differently. This resolves paradoxes by suggesting that every action in the past branches into a new reality, leaving the original timeline intact. While this theory is popular in science fiction, it remains speculative, as we have no direct evidence of parallel universes. Some physicists also explore quantum mechanics for answers. In particular, the concept of quantum superposition could allow for multiple outcomes to exist simultaneously, avoiding contradictions. In this view, a time traveler's actions might result in a quantum split, where different possibilities coexist without interfering with one another. While this idea aligns with certain interpretations of quantum mechanics, it's still far from being experimentally verified. Finally, there's the possibility that time travel itself might be constrained by physical laws we don't yet understand. Some theories suggest that time travel to the past might only be possible in very specific conditions, such as within closed time like curves or near exotic structures like wormholes. These conditions might naturally limit what a time traveler can do, preventing them from causing paradoxes in the first place. While we don't yet have definitive answers, these proposed solutions show that time travel, while paradoxical, might not be entirely impossible. They invite us to keep questioning the nature of time, causality, and the universe itself, pushing the boundaries of both physics and imagination. Chapter 5: The Technological Challenges. Section 1: The Energy Problem: Why it's almost impossible today. One of the biggest obstacles to making time travel a reality is energy. The sheer amount of energy required to manipulate space-time is beyond anything humanity can currently produce. From bending space-time for wormholes to overcoming gravitational forces near black holes, the energy demands of time travel are astronomical, literally. Let's take wormholes as an example. To create a stable wormhole, scientists theorize that we would need a form of exotic matter with negative energy density. This negative energy would be required to counteract the wormhole's natural tendency to collapse under its own gravity. While small amounts of negative energy have been observed in quantum experiments, scaling it up to the level needed for a wormhole would require vast amounts of energy, possibly equivalent to the total energy of an entire galaxy. Black holes present a similar challenge. While they naturally warp space-time, approaching a black hole to harness its gravitational effects would be incredibly dangerous. The energy needed to send a spacecraft to the edge of a black hole and keep it from being destroyed by tidal forces would far exceed our current technological capabilities. Even then, any attempt to use a black hole for time travel would likely require additional exotic materials to prevent destruction. Another theoretical approach to time travel involves accelerating an object to near light speeds. According to Einstein's theory of relativity, the faster you move, the slower time flows for you relative to someone at rest. However, as an object approaches the speed of light, its energy requirements increase exponentially. To accelerate even a small spacecraft to 99.99% of the speed of light, you would need an amount of energy comparable to the output of the sun over decades. For a larger object, or a human crew, the energy demand would be even more extreme. Practical considerations also come into play. How would we safely store and release such vast amounts of energy? Current energy storage systems, like batteries or fuel cells, are nowhere near sufficient. Even advanced nuclear fusion, often seen as a future energy solution, would fall short of meeting the requirements for time travel. Finally, there's the issue of controlling this energy. Even if we could harness enough power, the precision required to bend spacetime without causing catastrophic side effects would be staggering. Miscalculations could result in unintended damage to the surrounding environment, or worse, the creation of unstable spacetime distortions. In summary, the energy problem is one of the greatest barriers to time travel. While theoretical physics suggests it might be possible, the practical challenges of generating, storing, and controlling the required energy keep time travel firmly in the realm of science fiction, for now. Section 2: Materials and Engineering for Time Machines. Even if we solve the energy problem, building a time machine presents another significant challenge: the materials and engineering required to withstand the extreme conditions of time travel. Whether it's the immense forces near a black hole, the stabilization of a wormhole, or the construction of a device capable of manipulating spacetime, our current materials simply aren't up to the task. Let's start with wormholes. To keep a wormhole stable, scientists theorize that we would need exotic materials with negative energy density. These materials, often referred to as exotic matter, would need properties that defy the laws of classical physics, like creating a repulsive force strong enough to counteract gravity. While small-scale negative energy has been observed in phenomena like the Casimir effect, we are far from producing it in the quantities necessary for a functional time machine. Then there's the issue of strength. A time machine would need to endure the immense gravitational forces and radiation present near phenomena like black holes or neutron stars. Even the strongest materials we have today, such as graphene or carbon nanotubes, would likely disintegrate under such extreme conditions. New materials with unprecedented levels of strength, flexibility, and heat resistance would need to be developed. The engineering challenges are equally daunting. For instance, if we were to attempt time travel using near-light speed travel, the machine would face incredible pressures from the buildup of interstellar particles. These particles, even though tiny, would bombard the craft with enough energy to cause significant damage. A time machine would need to be equipped with shields, or mechanisms to deflect this particle radiation, technology that is currently far beyond our capabilities. Precision engineering is another critical requirement. Manipulating spacetime involves precise calculations and control, as even a tiny error could destabilize the machine or create unintended effects. For example, if a wormhole were to collapse during use, it could trap the traveler, or worse, cause catastrophic consequences for the surrounding spacetime. Building systems capable of handling such precision would demand a level of technological sophistication we have yet to achieve. Finally, the sheer scale of a time machine adds to the complexity. Whether it's a device designed to accelerate objects to near light speeds, or one capable of generating massive amounts of gravitational force, the infrastructure required would be enormous. Imagine building a machine the size of a city or larger. just to make the concept feasible. In conclusion, the materials and engineering challenges of constructing a time machine are as significant as the energy requirements. While these obstacles might one day be overcome, with advancements in material science and technology, they remain some of the biggest reasons why time travel is still out of reach. Section 3: The role of quantum physics. Quantum physics, the science of the incredibly small, could hold the key to unlocking the mysteries of time travel. While classical physics often runs into insurmountable paradoxes and energy barriers, quantum mechanics introduces new possibilities that challenge our understanding of time and causality. Could the strange rules of the quantum world make time travel feasible? One intriguing concept in quantum physics is quantum entanglement, a phenomenon where particles become interconnected in such a way that the state of one particle instantly affects the state of another, no matter the distance between them. This spooky action at a distance, as Einstein called it, suggests that information can travel faster than light, or perhaps even outside the normal flow of time. Some researchers speculate that entanglement could be a clue to understanding how time and causality operate on a deeper level, though practical applications remain purely theoretical. Another quantum phenomenon with time travel implications is quantum superposition. In this state, particles exist in multiple states or locations simultaneously until observed. This challenges the classical notion of cause and effect, as it implies that events can happen in multiple ways at once. Some scientists theorize that this could explain how timelines might branch or loop in the context of time travel, potentially avoiding paradoxes. Quantum mechanics also introduces the idea of closed time like curves CTCs. At the microscopic level, certain solutions to Einstein's equations suggest that spacetime could allow for loops where particles travel back in time. Quantum theorists propose that these loops might avoid paradoxes by adhering to probabilistic laws rather than deterministic ones. For example, if a particle were to travel back in time, quantum rules might ensure that it only interacts with its past self in ways that maintain consistency. Additionally, the holographic principle, a concept emerging from quantum gravity, suggests that all the information in a volume of space might be encoded on its boundary, like a 3D image projected from a 2D surface. This idea hints that time itself might be an emergent property, rather than a fundamental one. If true, manipulating time at the quantum level could involve altering how this hologram is projected, potentially allowing for new forms of time travel. Despite these exciting possibilities, quantum physics also raises significant challenges. One major issue is the observer effect, the fact that observing a quantum system changes its state. If time travel involves quantum processes, the mere act of interacting with the past could fundamentally alter the timeline, leading to unpredictable consequences. Moreover, combining quantum mechanics with general relativity, the theory governing spacetime, remains one of the biggest unsolved problems in physics, making it difficult to bridge the gap between theory and practice. In conclusion, quantum physics opens up fascinating new pathways for understanding time and causality, offering tantalizing glimpses of how time travel might work at the smallest scales. However, we are only beginning to scratch the surface of these possibilities, and much more research is needed before we can turn these theories into reality. Chapter 6: Theoretical Models of Time Travel. Section 1: The Multiverse Hypothesis and Parallel Timelines. The multiverse hypothesis is one of the most intriguing solutions to time travel paradoxes. It suggests that instead of a single, unchanging timeline. The universe splits into multiple parallel timelines whenever a significant event occurs. But how does this theory connect to time travel? And could it solve the problems posed by altering the past? In this model, each decision or change creates a new universe. For example, if a time traveler went back in time to prevent their grandfather from meeting their grandmother, they wouldn't erase their own existence. Instead, their actions would create a new timeline where they were never born, while their original timeline remains intact. This bypasses paradoxes like the grandfather paradox, as changes to the past don't affect the original timeline. The multiverse hypothesis is supported by certain interpretations of quantum mechanics, such as the many worlds interpretation. This theory suggests that all possible outcomes of a quantum event happen, but in separate, parallel universes. While this is a popular idea in science fiction, it remains highly speculative, as we currently have no way to detect or interact with parallel universes. However, the multiverse raises its own questions. If parallel timelines exist, how would a time traveler choose which one to enter? Could they ever return to their original timeline? And if infinite universes exist, is every possible version of reality equally real? These philosophical and practical issues remind us that the multiverse, while fascinating, is far from fully understood. In conclusion, the multiverse hypothesis offers a potential solution to the problems of time travel, but it also opens up a new set of mysteries. Whether these parallel timelines are real or just theoretical, they continue to inspire both scientific exploration and creative storytelling. Section 2: Loop Quantum Gravity, a New Frontier. Loop quantum gravity (LQG) is an emerging theory that could reshape our understanding of time and space. Unlike Einstein's general relativity, which describes space-time as a smooth fabric, loop quantum gravity proposes that space-time is made up of tiny, discrete loops. These loops, unimaginably small, form the fundamental building blocks of the universe. But what does this mean for time travel? At its core, loop quantum gravity aims to merge quantum mechanics with general relativity, a challenge that has puzzled scientists for decades. One of its most intriguing implications is that space-time itself might not be continuous. Instead, it could behave more like a woven tapestry, with individual threads forming a dynamic structure. If this is true, time, as we perceive it, might not be a smooth flow but a series of discrete moments stitched together. This idea opens up fascinating possibilities for time travel. In a universe governed by LQG, space-time might have shortcuts or loops that allow for connections between different points in time. These shortcuts wouldn't behave like the smooth wormholes described in traditional relativity, but would instead rely on the quantum nature of space-time itself. While this remains theoretical, it suggests that time travel could be possible within the framework of quantum gravity. LQG also has profound implications for the nature of time itself. If time is quantized, divided into the smallest possible units, then the traditional arrow of time might not be as fixed as we believe. Some researchers speculate that this could allow for time to loop or reverse under certain conditions, though the exact mechanisms remain unclear. Despite its promise, loop quantum gravity faces significant challenges. The theory is mathematically complex and difficult to test experimentally. Unlike general relativity, which has been validated through observations, like gravitational waves, LQG's predictions occur at scales far smaller than anything we can currently measure. However, ongoing research in fields like black hole physics and cosmology continues to provide indirect evidence that supports the theory. In summary, loop quantum gravity offers a bold new perspective on time, space, and the universe. While it's still in its early stages, its potential to unlock the secrets of time travel makes it one of the most exciting frontiers in modern physics. If we can one day understand and harness the quantum fabric of spacetime, the dream of time travel might move closer to reality. Section 3. Is time travel already happening in small scales? While time travel might seem like a distant dream, some scientists believe that it could already be happening, but only on the smallest scales. Quantum mechanics, the science of the very small, reveals behaviors that challenge our classical understanding of time. These strange phenomena may hint at forms of time travel, occurring in ways we can't yet observe directly. One fascinating example is quantum tunneling, a process where particles seem to jump across barriers without passing through them. In this process, particles appear to bypass the rules of classical physics, almost as if they are skipping forward in time. While this isn't time travel in the traditional sense, it demonstrates how quantum systems can defy our normal understanding of cause and effect. Another potential example is retrocausality, the idea that future events can influence the past. Some interpretations of quantum mechanics suggest that particles in entangled states might exchange information in ways that appear to violate the normal flow of time. For instance, experiments have shown that the measurement of one entangled particle can instantly affect its partner, even if they are separated by vast distances. This spooky action raises the question: could quantum processes allow for limited forms of backward causation? Additionally, closed time-like curves (CTCs), which are solutions to Einstein's equations, may exist on microscopic scales. While they are purely theoretical for now, some researchers speculate that tiny loops in spacetime could allow particles to interact with their past or future selves. If proven, this would be a form of time travel, albeit limited to subatomic particles. Even black holes provide clues. Near the event horizon of a black hole, the intense warping of spacetime creates extreme conditions where quantum effects dominate. Some theories propose that particles interacting in this region might experience time in ways that differ drastically from our everyday experience. Although these phenomena are fascinating, they remain confined to the quantum realm and don't translate to larger systems like humans or spacecraft. Scaling up quantum effects to macroscopic levels would require breakthroughs in both technology and our understanding of physics. For now, quantum time travel remains a tantalizing glimpse of what might be possible. In conclusion, while time travel on a human scale remains out of reach, the quantum world offers compelling evidence that time behaves very differently at microscopic levels. These small-scale effects may one day provide the key to unlocking time travel for larger systems, but only if we can fully grasp the strange and mysterious rules of quantum mechanics. Chapter 7: The Philosophical Implications. Section 1: What time travel would mean for humanity. Time travel is more than just a scientific possibility, it's a concept that would fundamentally reshape how we understand our place in the universe. If humans could travel through time, it wouldn't just change science. It would challenge our ethics, culture, and even our sense of identity. Let's explore what time travel could mean for humanity as a whole. One of the most profound implications of time travel would be the ability to observe history firsthand. Imagine witnessing the rise and fall of ancient civilizations. or seeing iconic moments like the signing of the Declaration of Independence or the construction of the pyramids. Time travel could make history more tangible, providing clarity about events that remain mysteries today. However, it also raises concerns about altering the past. Even the smallest interference could ripple through time, changing the course of history in ways we cannot predict. The potential to travel into the future is equally exciting. It could allow us to glimpse humanity's long-term destiny, whether it's the colonization of distant planets, the discovery of new technologies, or the challenges we may face, like resource scarcity or climate change. This foresight could inspire us to make better decisions today, but it might also create ethical dilemmas. If we knew about future disasters, would we feel obligated to prevent them, even if it meant drastically altering the timeline? Time travel would also force us to rethink personal responsibility. If the past and future are accessible, does free will truly exist? For example, if future historians came back to study us, would we feel compelled to act differently, knowing our actions were being observed? The knowledge that time is malleable could have profound psychological effects, making us question whether our choices are our own or part of a predetermined timeline. On a broader scale, time travel could redefine how we interact with the universe. It might enable humanity to escape catastrophic events, such as a dying sun, by jumping to safer points in time. Alternatively, it could help us discover alien civilizations by exploring distant areas of the cosmos. However, this also raises the question of who would control such technology. Would time travel be reserved for the elite, or would it be accessible to everyone? Ensuring fair and ethical use of time travel would be one of humanity's greatest challenges. In summary, time travel could unlock incredible opportunities for exploration, knowledge, and survival, but it also comes with significant risks and ethical dilemmas. It would force us to confront difficult questions about our actions, our responsibilities, and the very nature of existence. While the science of time travel remains theoretical, its implications for humanity are vast and worth considering. Section 2: Ethical concerns of altering history. If time travel became a reality, one of the most difficult challenges humanity would face is managing the ethical implications of altering history. Changing even a single event in the past could have widespread, unpredictable consequences for the present and future. This raises critical moral questions: should we interfere with history? And if so, under what circumstances? One major concern is the butterfly effect, the idea that small changes in the past can lead to dramatic, unforeseen consequences over time. For example, saving one individual from an accident might inadvertently prevent future generations from being born or alter critical historical developments. While such changes might seem minor at first, they could snowball into outcomes that no one could have anticipated. Another ethical dilemma involves the question of whether we have the right to change history at all. Would it be acceptable to go back and prevent catastrophic events like wars or natural disasters? While this might seem like an obvious good, it raises concerns about who gets to decide what should be changed. Different cultures and perspectives may have conflicting views on which events should remain untouched and which should be altered. The ethics of erasure is another pressing issue. If history is rewritten, does that mean the original timeline is effectively erased? Billions of lives and experiences could be wiped out, raising the question of whether it's ethical to sacrifice one timeline for the sake of creating another. For those who lived in the original timeline, this would be equivalent to erasing their very existence. Time travel could also introduce power imbalances. If the ability to alter history fell into the hands of a select few, they might manipulate the past for personal or political gain. This could create a dystopian scenario where history is rewritten to favor specific groups or ideologies, effectively erasing opposing voices and perspectives. Finally, there's the question of responsibility. If time travelers make changes that result in negative consequences, who should be held accountable? Would the blame lie with the individual traveler, the organization overseeing the technology, or the society that allowed it to exist? Establishing clear ethical guidelines for time travel would be essential to prevent misuse and minimize harm. In conclusion, the ethical concerns of altering history highlight the immense responsibility that would come with time travel. While the power to change the past might offer incredible opportunities, it also carries the risk of unintended consequences and moral dilemmas. Before humanity takes such a step, we must carefully consider not just what we can do, but what we should do. Section 3. Could time travel change the future of science? If time travel became possible, it wouldn't just revolutionize our understanding of physics. It could transform every field of science. From unlocking the mysteries of the past to predicting the future, time travel has the potential to reshape how we study the world and expand the boundaries of human knowledge. One of the most immediate benefits would be in historical and archaeological research. Scientists could travel to key moments in history to observe them firsthand, solving long-standing mysteries. Imagine witnessing the construction of the pyramids, or uncovering the truth behind extinct civilizations like the Mayans. Such discoveries would fill in gaps in the historical record and provide insights into humanity's evolution and cultural development. Time travel could also revolutionize medicine. Researchers might travel to the future to access advanced treatments, technologies, or even cures for diseases that plague humanity today. Conversely, they could visit the past to study diseases that have since been eradicated, offering new perspectives on how pathogens evolve and how pandemics can be managed more effectively. In physics and cosmology, time travel would allow scientists to test theories that are otherwise impossible to verify. For instance, they could observe the Big Bang, or explore the early moments of the universe to gain a deeper understanding of how everything began. Similarly, traveling to the future could help researchers confirm predictions about the fate of the universe, such as the expansion of space or the ultimate heat death. Another fascinating application lies in climate science. By visiting different points in Earth's history, scientists could study ancient ecosystems, track environmental changes, and refine models for predicting future climate scenarios. This could lead to more accurate strategies for combating climate change and preserving biodiversity. However, time travel's impact on science wouldn't come without risks. Observing or interacting with the past could inadvertently alter the timeline, leading to unexpected consequences. There's also the ethical question of whether it's right to take knowledge from the future or interfere with historical events, even in the name of science. Additionally, ensuring that time travel is used responsibly would require global cooperation and regulation, much like today's guidelines for genetic research or nuclear technology. In conclusion, time travel has the potential to revolutionize science in ways we can barely imagine, offering answers to some of humanity's greatest questions. However, it would also demand careful consideration of the ethical and practical challenges it presents. If we ever unlock the secrets of time travel, it could mark the beginning of a new scientific era, one where the boundaries of time itself are no longer a limitation. If you found this video helpful or interesting, please give it a thumbs up and subscribe to the channel.